All right, ladies and gentlemen, so let's get started. For this week, we have invited Mr. Alireza Sheikhattar. Let me give a very brief introduction for Alireza. He got his bachelor degree in electrical engineering from Sharif University of Technology in Iran in 2011. And he got his master degree for electrical engineering from University of Maryland in 2014. And he is now a PhD candidate. He's going to tell us something about I think he's going to tell something about the signal processing for how to do dynamic estimation of causal influences in sparsely interacting neural ensembles. So let's give the time to Alireza.
Thank you. As he introduced me, I'm Alireza, and my title of talk today is Dynamic Estimation of Causal Influences in the Sparsely Interacting Neuronal Ensembles. We start with the notion of causality in neuronal signal processing. As you know, it is known that signals in the brain they exert causal influences on spiking activities of the surrounding neurons, and the detailed analysis of these causal interactions can improve our understanding of how groups of neurons cooperate together to generate a specific brain function. One of the most effective methods for causal analysis is Granger Causality. The Granger Causality is a powerful statistical tool for causality inference in time series analysis, which has a wide range of applications, which is used in a wide range of applications. More recently, the Granger Causality has become increasingly popular in the context of neural signal processing and computational neuroscience, where it is used to infer causal interactions from simultaneously recorded neural data recordings, which can be any continuous value neural data, such as MEG, EEG, local field potentials, or fMRI, or any discrete value data, such as multi-unit or single-unit recordings. The idea of Granger Causality is originally proposed by Wiener back in the 50s, based on the temporal predictability, and later formalized into the practical form by Clive Granger. The basic idea is pretty simple, that given two data sequences X and Y, if including the history of Y can improve the prediction of X, we say that there is unique information from Y into X that is not containing other explanatory covariates. So we say that Y has a Granger causal influence on X. Several causality analysis methods have been proposed in the literature for spiking data activity. They have several shortcomings, such as most of these methods, they do not take into account the discrete nature of the neural spiking activity. And most of them, they're more useful for models with linear regression and linear Gaussian statistics. And they're not applicable for highly non-Gaussian data, such as spiking data. And also, most of them, they provide static estimates of causality throughout the whole period. And so they cannot capture the dynamics of the causality along the time. As I said, most of the Granger causalities, they're based on autoregressive modeling, which is more useful for stationary environments. And but as we know, most of the neural data recordings, such as fMRI, MEG, EEG, they exhibit at least a degree of non-stationarity in time with parameters that are changing, and the underlying parameters that are changing in time. Such non-stationarity can be explained, it can be implied that maybe the causal interactions are varying in time. One of the most powerful Granger Causality measures that's proposed in the literature is likelihood-based Granger Causality measure that's based on, proposed by Kim, that's based on the point process framework, which is directly applicable to discrete neural data, neural spiking activity of neural ensembles. In this slide, we consider a neural ensemble under spontaneous activity where each neuron is modulating the spiking activity of other neurons through its history. And based on the natural parsimony of the neurophysiological signals, we assume a sparse representation for the cross-history dependence between the neurons. The main goal for this talk is the adaptive identification of the dynamic causal interactions among neurons from the spiking data in a recursive online fashion, so we can use it as a real-time algorithm. To this aim, we introduced a novel time-varying measure of Granger causality, which is suitable for adaptive setting. And we will design a low complexity adaptive filter, a fully recursive algorithm for computation of this new Granger causality measure. And we will develop a statistical inference framework based on the analysis of deviance. This statistical inference is useful to identify the potential causal interactions between neurons. In the next, we will derive a Noncentral chi-squared filtering and a smoothing algorithm to estimate and track the dynamics of causal interactions. And at last, we construct a statistical confidence regions for the estimated causality measures. In this slide, we will shortly describe the theoretical background of the sparse adaptive filtering algorithm that we proposed earlier in our earlier work. We modeled the neural spiking, the binary valued neural spiking activity with Bernoulli process, the conditional Bernoulli point process model, where the spiking activity, the spiking probability, which is denoted by lambda k delta, is modeled by a dynamic generalized linear model, or GLM, with a logistic link function. We have denoted the sparse time varying vector by omega k and the covariate vector by xk. We modified the standard log likelihoods into the adaptive form based on the forgetting factor mechanism of the well-known class of recursive least square algorithms, where we use the exponential weighting for the log likelihoods. As you see that we have denoted the forgetting factor by beta, and the likelihoods by small l, as you see here. And for adaptive estimation of the modulation parameters, we solve a sequence of recursive regularized maximum likelihood problem at every time k, as you see here, and which can be efficiently solved using proximal algorithms or coordinate descent algorithms. So for this work, we employ the sparse adaptive filters that we have derived in our earlier works for recursive estimation of these time-varying parameters, such as the filters L1 PPF1 or greedy filter, sparse greedy point process filter in our earlier work. For this talk, we start with the time-varying Granger causality measure that we will propose. The classical Granger causality measures, they're more expressed in terms of multivariate autoregressive models, But the more modern version of Granger causality is based on likelihood, established based on the log likelihood ratio statistic. Unlike the classical Granger causality, which is specialized more for the for the models with linear Gaussian statistics, the new Granger causality measure benefits from the likelihood inference. So it can cover a broad range of statistical models, such as the point process model that we like. So it can be applied to neural spiking activity. We have denoted the log likelihood ratio statistic associated to causal influence of neurons T to neurons T in the following form, with which you can see the log likelihood ratio, the log of ratio of likelihood of the full model, which we denoted by C, to the reduced model. Based on this formulation, the Granger causality measure is measured as a reduction in point process log likelihoods of neuron C for the reduced model compared to the full model, where the reduced model we have excluded the historic covariates associated with neuron C tilde. As you see, even though it's based on likelihood and it's favorable, but it's still a static measure, which is just suitable for stationary and static data. What we need a dynamic version of this. In order to extend it to dynamic version, we will introduce a novel time-varying Granger causality measure, which give us the capability to track the dynamics of causality interactions in time. In order to induce adaptivity into this measure, we will leverage the RLS-inspired forgetting factor mechanism. So we replace the standard data log likelihoods by the adaptive log likelihoods that we proposed earlier, based on the RLS, and which we in the new dynamic Granger causality measure we've shown on the bottom part. As you see, it is. It's shown by the reduction in log likelihoods of the full model and reduced model, and as you see, you have a scale. It denotes the sign factor that just determines the inhibitory or excitatory nature of the underlying causal interaction. In order to compute this Granger causality measure in a recursive form, we exploit the RLS type exponential weighting of the data log likelihoods. We develop a low complexity update rule for the adaptive log likelihoods that we proposed earlier, and consequently for the new Granger causality measure. To this aim, we exploit the smoothness of the point process log likelihood, and we use the second order Taylor series expansion approximation for that. As you see here in this relation, that we use the second order Taylor series for each time k, and as you see, we have shown the gradients and Hessians by L dot and L double dot. By computing the gradients and Hessians for the logit link point process log likelihoods, and in substituting that in this quadratic approximation, we will come to the recursive formulation for the log likelihood, as you see, for the adaptive log likelihood as you see here, which is composed of a scalar valued AK, vector bk, and a matrix with large bk. As you see, we have derived a recursive formulation for all the parameters. So it can, and all these recursive formulations are low complexity. As you see, for the matrix, it's just a rank 1 update. We have summarized all the recursive procedure in this code here. By performing these iterations for both the reduced and full model, we will achieve a fully recursive update procedure for the new Granger Causality measure that we propose. This can enable us to track the causal interactions in an online mode, real-time mode. But the problem is that due to the noisy and biased nature of these estimates, the non-zero values of these Granger causality measures that do not necessarily imply the existence of causal interactions. So they need some statistical test. So it is required to investigate the statistical significance of the recursively computed Granger causality measures we will use an analysis of deviance. What is deviance? Deviance statistics is a likelihood-based measure which is widely used for statistical inference of the generalized linear models, GLMs, which it generalizes the concept of residual sum of the squares for ordinary linear regression models. It can be shown as you see the definition of the deviance is twice the log-likelihood ratio of any fitted models compared to saturated model. And what we like here is that the proposed Granger causality measure that we had earlier can be expressed in form of the deviance difference of the full and reduced model as you see here. The deviance difference statistic is shown as being proven as an effective statistical measure for assessing the discrepancy between any two fitted models, which has shown to be very useful in particular in the case of nested GLMs, where the reduced model is just a special case of the more complex full model, which is exactly in our case.
So when beta goes to 1, that means there is no forgetting factor, right? So
no, it's not no forgetting factor. Oh, you mean in the bottom? We reached that right now. It's just asymptotic. It's some asymptotic result. When beta approaches to 1, we have some asymptotic distribution. And so our approach to the statistical inference is based on asymptotic distribution of the deviance difference statistic. We proposed an adaptive version of deviance, as you see here, and we extend the classical asymptotic results in the literature to the adaptive setting. Based on the classical results in asymptotic distributions by Davidson in 1970. The deviance difference asymptotically follows a non-central chi-square distribution under certain regularity conditions as forgetting factor approaches to 1. But this version we have adopted the classical version to the forgetting factor adaptive version that we like. And we have proven this that the new proposed deviance it will approaches in distributions to a non-central chi-square distribution. As you see, MD is degree of freedom for non-central chi-square, which denotes the dimensionality difference of two nested models, full and reduced models. And the new K shows the non-centrality parameter. The non-centrality parameter plays a crucial role in the statistical inference procedure that we will introduce. Because the small values of nu k, the small values of the non-centrality, it can be implied that there exists no source of deviance between the full and reduced models. So it can be inferred there is no causality between associated neurons. And the significant values of nu k or non-centrality, it can be implied that there exists a significant deviance between the more complex full model and the reduced model. So it can be implied that there is a causal link between the associated neurons. So as you see, we change the role of deviance, the noisy deviance, to the non-centrality. We propose estimation model for the non-centrality. We want to estimate the non-centrality based on the observed deviance data decay. Because the non-centrality just take non-negative values, we choose exponential. We choose the non-centrality to be exponentially linked to a state variable zk with first order AR dynamics, as you see here. And rho is just a gain factor between 0 and 1, and EK is the noise of the state space model with a Gaussian zero mean and variance sigma squared of E. We will propose a non-central chi-squared filtering and smoothing algorithm, which is composed of 3 main parts: a forward non-central chi-squared filter, backward fixed interval smoother, and an expectation maximization step. The first one is forward non-central chi-square filtering. We start with that. Based on the unimodal property of non-central chi-square non-central chi-square distribution, we make a recursive Gaussian approximation to the posterior density function, and we recursively compute the posterior modes and posterior variances, which we denoted here with zk given k and sigma squared k given k in recursive mode. As you see, the relations below, the derivations are too messy. Which is, as you see, it contains the Bessel functions of the first kind, the modified Bessel functions of the first kind, with order alpha. And then we'll go to backward filter, backward fixed interval smoother. Given the filtered estimates, now we can perform backward smoothing based on the fixed interval smoothing algorithm that is proposed in the literature. And we compute the smooth posterior modes and variances in a backward fashion. And after that, it's really easy to compute the statistical confidence regions for both filtered and smooth estimates based on the assumption that we had that we have Gaussian approximation for each time k, and as you see here, it's basically a confidence region based on Gaussian approximation, and the easy part is because of the monotonicity of exponential link. So we have derived easily a method for statistical confidence regions for along the time, across the time. And finally, we will estimate the state variance, optimal state variance, based on the complete set of the deviance data that we have, using the expectation maximization method or EM method. We take the details is just we take the state variable that we defined earlier as the latent variable, and after we do the E step and M step, we will come up with the relation that's stated here. And we can repeat that to estimate the optimal variance, the optimal state variance that we defined earlier. Here we come to the application of our algorithm. First, we'll apply it to simulated data, then on the real data. Consider two binary valued spiking data synthetically generated by the simulation based on a network of two neurons that I've shown here, neuron 1 and neuron 2. As you see, the excitatory and inhibitory relations has been shown with the black and white circles. As you see in this network of two neurons, there is two self-inhibition for neuron 1 and neuron 2, and a causal excitatory link from neuron 2 to neuron 1 that is evolving along the time. As you see, it's in this along the time, it's weakening, and the third segment of the experiment is totally gone. After what we use for model is we assume sparse modulation vectors for the both neurons as omega k1 and omega k2. The omega k1 has omega k11 and omega k12. Omega k11 is denotes the self-inhibitory effect, and omega k12 is the main one that shows the cross-history dependence of the neuron 1 and neuron 2, or which represents the causality. And omega k22 is the self-inhibitory for the neuron 2. We have shown these three sparse vectors here. In order to model the dynamic causal link, we simply enforce a time evolution on the in support coefficients of the omega k12 that was corresponding to causal link. We just use a simple time evolution that in the first segment of the simulation it remains constant. In the second segment, on all these two inhibitory in support coefficients, they decline to 0, and in the third segment they remain 0. For the sparse adaptive filter, we use the L1-PPF1 that we proposed in our earlier work to estimate omega k for both full and reduced models. In this figure shows, as you see in this figure, there are 3 segments and spiking data. These 4 figures that you see, figures C and D, they represent the time course of changes that is detected based on the using our algorithm non-central cholesterol filtering. You had a question?
Yeah. So the spiking data that you generated is by simulating a Bernoulli process?
Yeah, it's basically, as I shown in theoretical background, it's a conditional Bernoulli point process model. Okay. Based on
and the omega values you are pre-deciding.
Yeah, I'm choosing omega values to as you see you see in this figure. These omega values is just a sparse model.
Omega is the parameter of your.
Yeah, it's exactly the tuning parameters that tuning the behavior dynamics of the neurons.
Okay. And omega changes with time.
Just as you said, just I enforced the time evolution just for omega k12, but omega k11 and omega k22 that are just self-inhibitory effects of neuron 1 and neuron 2, they remain constant. They can change, but I just wanted to show how we can track the causality changes. The part that corresponds to causality is omega k12. Omega k12 is the cross-history dependence of neuron 1 based on neuron 2. So if neuron 2 begins to spike or not spike, it has some effect on neuron 1 based on these tuning effects.
What are these 3 plots? 3 different things?
Sorry?
What are the 3 plots?
Oh, the 3 plots. Maybe you can see. On the first plot, you see the omega k11 as it has 50 coefficients, just 3 non-zero. It's sparse. Sparse, 3 non-zero coefficients, 50 out of 50, total 50 coefficients. And the omega k12 also sparse, 2 non-zeros, the support of that is just 2 coefficients. And omega k22 we chose the sparse with 3 coefficients.
Okay.
It's just you can choose any sparse coefficient.
So if you use 50 coefficients, that means a history of 50 dependence.
These three parameter vectors, they, if I go back, let's go back one time. You see here, lambda k delta is equal to logic linked xk transpose omega k. This will is some kind of logistic link. On xk is a covariant vector that is all historic components of the neural spiking activities of neuron, self neuron, and other neurons. And the omega k is the sparse time varying vector that we want to estimate, but in our synthetic we will choose it and then estimate it.
Okay.
You get it. And as you see here in the you see the detected time course of changes that we have detected from the Granger Causality. For the panel C and D, it represents the detected changes of causal influence from neuron 2 to neuron 1 that was existing and changing. And E and F shows the vice versa, from neuron 1 to neuron 2. As you see in panels E and F, our algorithm has avoided the false alarm detection and estimated the causality. Let me say that the blue trace shows the filtered estimates. The red trace shows the smooth estimates, and the black noisy thing is the deviance data that we have computed. As you see, the red and blue one, you see the excellent performance of our algorithm that it avoided the false alarm detection and estimated the nu hat k as 0. So it implies that there is no causality from 1 to 2. That was exactly correct. We have causality from 2 to 1. And from panels C and D, you can see that our algorithm have done a pretty good job at identifying the Granger causality and tracking the changes along the time. As you see in the first segment, it's going up, and in the second segment, it has detected that the causality link is weakening to 0, and in the third segment, it has detected that it's totally vanished. And you see that our algorithm has done pretty well.
How do you choose your beta and the regularization parameter?
The beta we have chosen, as you see, it should be comply with the asymptotic result. It should be enough close to 1. So we chosen 0.9999.
Okay.
And for gamma, you mean gamma? The other one, the regularization. The regularization, we use the twofold even odd cross validation to compute it based on data.
Can you point out the false alarm in this plot?
The false alarm?
Yeah.
You see that we've shown E and F. Let me say that you see 4 figures because we have shown it in 2 different smoothing regimes. In E and F, what we show here is the detected or estimated causality from neuron 1 to neuron 2, as you see in the axis, in the vertical axis. From neuron 1 to neuron 2. The non-central chi-squared filtering and smoothing algorithm that we have proposed, as you see, it has estimated it as 0. So there is no, even though that sometimes in the first part, the deviance was greater than 0, but our filtering and smoothing algorithm avoided false alarm. There are many situations that other algorithms in the literature, they do false alarm. They have the error false alarm detection error that is really many algorithms that have that problem.
Okay.
As you see, we have estimated when nu hat k is when non-centrality is estimated as 0, it implies that there is no causality between 1 to 2. But when as you see, we have estimated something very really significant as 100 to 200 in the first panels, that there was causality, then diminished linearly to 0 and 0. In the last part of our talk, we say how we explain how we applied our algorithm to the real data. We applied our algorithm to real data to infer causality between two cortical areas of ferrets, one from prefrontal cortex, one area of prefrontal cortex, and another the primary auditory cortex, or A1, in single unit level, or I mean that we use spiking data. And in this experiment, the single unit activity and local field potentials are recorded simultaneously in these two regions, A1 and PFC, where during a series of passive and active auditory tasks. The ferrets, as you see, the animal on the top part, the ferrets were trained to attend and discriminate between two tones. They were hearing, they were discriminating by behavior between two tones. And what we wanted to infer, we wanted to infer the causality between the PFC, neurons in PFC and neurons in the A1 region, as you see on the top. There were 4 neurons detected in PFC, 1 neuron in A1. We analyzed all pairwise possible links between 1, 2, 3, 4 to 5, and I've shown that we have found a significant causality from neuron 4 to neuron 5, which is from PFC to A1, during the 90-second time, and but we didn't find causality in other links. We found causality from 4 to 5, which this is consistent with the top-down link from prefrontal cortex to the auditory cortex.
So 1, 2, 3, and 4 correspond to 4 different regions?
No, 1, 2, 3, 4. Just there's 4 single units, 4 cells.
Wow.
It's really hard to find causality between cells. It's easy to find causality in LFTs because LFTs are combination of hundreds or thousands of neuron populations, but it's really hard to find. You should look for it to find just a pair that has some causality. As if you in the literature there is no causality method that you can find that it can be applied to single unit level. It can't detect a single unit level. It just detects the LFPs, the causality between LFPs. You see that our algorithm can have identified a time-varying causal link in the top panel from PFC to the A1, you see from another neuron in PFC to A1, it has detected 0 causality. The conclusion is we propose a novel time-varying Granger causality measure, and developed a fully recursive algorithm for computation of that Granger causality measure, and we next developed a statistical inference framework for identification of causal interactions. We derived a non-central chi-square-filter smoothing algorithm for estimating of the dynamic causal influences with high temporal resolution. And our future work is we want to extend the proposed Granger Causality method to LFT and LFT spike, because our method is right now based on spike and spike, and we are trying to extend it to more data, more neural data modalities. And I want to acknowledge from my advisor, Dr. Bektash Babadi, and thank you.
Thank you.
Do you have any questions?
Yeah.
Any question?
So, just as a broad, big picture, what are you trying to achieve? Are you trying to get a synthetic model of neuronal activity?
Not a synthetic model for neural activity. We, as I told in the first part, the inferring causality between neurons, the interactions, the causality interactions between neurons, neural populations of neurons, is really important in computational neuroscience.
Right.
If you can infer causality between neurons, or you can detect the causality changes in time, it can give you, it can gain insight, really good understanding of how different brain functions are really working. For example, if you are for this decision making or working memory or any in your mind you're thinking how neurons are interacting with each other, which neural population is causing another neural population to fold or spark. For example, inhibitory effect will not spark in some time or spark in some time.
So based on like if you have some collected data from neurons, and if you compute the Granger causality from the data that you have, so you can basically construct networks of neurons.
Yes, it's more than networks. It's really better than networks because some works are done to just infer networks. It's named more. It's referred to as functional connectivity. In functional connectivity, you don't have directional influences, but in causality, you have directional, from neuron 1 to neuron 2, or from population 1 to population 2, or brain region 1 or brain region 2. When it's directional, it's really more exciting. You can see that, for example, one part, as you see, prefrontal cortex can cause something in the auditory cortex. You can infer causality between different, and the part that is more exciting is the part for after you infer causality, the neuroscientists work on the discussion.
Right.
What does it mean that this part is working on this part?
Right. So your whole work is based on the assumption that the neuronal data is a Bernoulli process.
Sorry?
Your neuronal data is a binary point process. Bernoulli point process.
It can be modeled very well with a binary. It's not just a binary point process.
Bernoulli.
Yeah, it's not just Bernoulli process.
Oh, okay.
It's more complex than Bernoulli process. It's conditionally Bernoulli point process. Point process is some extension of Poisson process. Mm-hmm. And it's based on some assumptions, it can be approximated as conditional Bernoulli process.
Okay.
Yeah. But it's working with Bernoulli process.
So that is an accurate model for neural activity.
It's doing pretty well in many.
That is what
you can't find a model that works on early neural data.
Right.
It's pretty good for spiking data.
Okay.
Yeah. We have applied it to mostly to auditory cortex because we have cooperation with the Sheikhattar Jonathan lab.
Mm-hmm.
Yeah.
Thank you.
Thank you. Any more questions? Thanks.